Why haven't we found aliens yet? Hundreds of billions of galaxies, each galaxy containing hundreds of billions of stars, and orbiting them, trillions of planets. The numbers are impossibly large. In our Milky Way galaxy alone, scientists estimate there are at least 40 billion Earth-sized planets within the habitable zone, where liquid water could exist. 40 billion. It's a ridiculously crowded universe. And yet, when we listen, all we hear is silence. Have you ever looked up at the night sky and felt alone? That feeling isn't just yours. It's one of the biggest, most terrifying paradoxes in modern science. This is the World Mystery Exploration Channel. And today, we are digging deep into the question, where is everybody? Why haven't we found any sign of alien life? This question is so famous it has its own name, the Fermi Paradox. In 1950, during a casual lunch, the brilliant physicist Enrico Fermi asked a simple question. If the universe is so vast and so old, and life should be relatively common, then why don't we see evidence everywhere? Think about it. Our sun is a relatively young star. There are stars billions of years older than our Earth. Imagine a civilization that is just 1 million years ahead of us, a cosmic blink of an eye. They would have likely mastered interstellar travel. They could have colonized the entire galaxy, multiple times over. We should see them. We should be picking up their radio signals, seeing their massive engineering projects, or at least finding their robotic probes. But there's nothing, just the great silence. What does this mean? Scientists have proposed numerous hypotheses, and every single one is mind-bending. Why is the universe so quiet? We will explore 4 main hypotheses, ranging from the concerning to the truly terrifying. First, Hypothesis 1. The Great Filter. Have we passed it, or is it waiting for us? This hypothesis suggests there is an invisible barrier or filter that all life must overcome to become an interstellar civilization. There are 2 scenarios. Scenario 1, good for us. The filter is behind us. Perhaps the emergence of life itself, or the evolution from a simple cell to a conscious being, is extremely rare. Maybe we are the first or the only civilization in our galaxy. We got lucky and passed the filter. Scenario 2, very bad for us. The filter is in front of us. This is the scary one. It means that all civilizations, upon reaching a certain technological level, like where we are now, inevitably face a self-destructive catastrophe. Maybe it's nuclear war, irreversible climate change, or an out-of-control AI. Or in other words, the universe is silent, because no one survives long enough to leave their home planet. Second, Hypothesis 2. The Dark Forest. They are hiding. This is a chilling hypothesis, popularized by novelist Cixin Liu. It compares the universe to a dark forest at night. In this forest, every civilization is a hunter with a gun. What is the ultimate survival rule? Stay silent. Anyone foolish enough to reveal themselves to light a campfire, like we are doing by sending radio signals into space, will be instantly spotted by other hunters and eliminated. Why eliminate? Because you can never know the intentions of another civilization, and the technological gap could be absolute. The safest bet is to pull the trigger first. According to this hypothesis, aliens exist. They are everywhere, but they are holding their breath, hiding in the dark, and the silence we hear isn't loneliness, it's fear. Third, Hypothesis 3. The Zoo Hypothesis. They are watching us. This one is less terrifying, but rather condescending. It suggests that advanced civilizations already know about us, but they treat Earth as a nature reserve or a zoo. They observe us from a distance, much like we observe an uncontacted tribe in the Amazon, or a pride of lions in Africa. They may have agreed on a prime directive of non-interference, waiting until humanity matures technologically and ethically. We simply aren't interesting enough or advanced enough for them to make official contact. We are just an experiment being monitored. Fourth, Hypothesis 4. They are too alien. We are looking for the wrong things. Perhaps the biggest problem is us. We search for life like us. We listen for radio signals. We look for Earth-like planets. But what if life out there is fundamentally different? What if they are a silicon-based collective consciousness? What if they are energy beings living inside stars? What if they communicate using gravitational waves or neutrinos that we can't yet decipher? It's like trying to explain the concept of the internet to an ant. The ant might crawl over a fiber optic cable every single day, but it will never comprehend the information streaming through it. Maybe we are surrounded by life, but our brains and our tools are simply too primitive to recognize it. From the Great Filter, the Dark Forest, to the zoo hypothesis, every answer to the Fermi Paradox opens up a vista that is both terrifying and magnificent. Right now, space telescopes like James Webb are peering deeper into the cosmos, analyzing the atmospheres of distant planets for signs of life. The answer might come sooner than we think, but whatever the final answer is, it will change humanity's perception of itself forever. If we are truly alone, it makes Earth and every life on this planet infinitely precious and fragile. The responsibility to protect this flame of consciousness is ours alone, and if we are not alone, then a great or terrifying new chapter is waiting for humanity out there, among the stars. The question, where is everybody, is really a question about ourselves. Who are we in this vast cosmos? What do you think? Which hypothesis do you find most compelling? Are we the lucky few, or are we just children in a forest full of danger? Leave your comments below. Why is 95% of the universe invisible? Take a look outside on a clear night. What do you see? You see stars, perhaps a planet, and the glowing band of our own Milky Way galaxy. If you use a telescope, you see other galaxies. Beautiful, swirling islands of light, each containing billions of stars, planets, and gas clouds. All of this, every star, every planet, every asteroid, every grain of dust, and every living being on Earth is what we call matter. This is the stuff of the universe. Now, what if I told you that everything I just mentioned, everything we have ever seen, measured, or touched, makes up only 5% of the total universe? It's one of the most profound and humbling facts in all of science. 95% of our reality is invisible. It is not made of the same stuff as us. It is not atoms. It does not glow. It does not reflect light. It does not block light. It is a dark majority that, until recently, we didn't even know was there. This 95% is the ultimate cosmic iceberg. We are living on the tiny, visible tip, while an enormous, unseen mass lurks below. So, what is this invisible 95%? And if we can't see it, how on earth do we know it even exists? This is not one mystery, but two. The invisible 95% is made of two completely different and equally bizarre substances: dark matter and dark energy. Let's start with the one we discovered first. Dark matter. Dark matter accounts for about 27% of the universe. It is the invisible glue that holds the universe together. We can't see it, but we can see exactly what it does. The story begins in the 1930s with an astronomer named Fritz Zwicky. He was observing the Coma cluster, a massive collection of galaxies. He measured how fast these galaxies were moving. What he found was shocking. The galaxies were moving so fast that the gravity from all their visible stars and gas shouldn't have been nearly enough to hold the cluster together. By all calculations, the cluster should have flown apart, with its galaxies scattering into deep space. Zwicky proposed that there must be some form of unseen, dark matter, or dunkle materie as he called it, that was providing the extra gravitational pull needed to keep the cluster intact. At the time, his ideas were largely dismissed. The smoking gun evidence arrived decades later in the 1970s from the work of astronomer Vera Rubin. She was studying the rotation of individual spiral galaxies, like our own Andromeda. She expected to find something simple. Just like in our solar system where the inner planets move fast, like Mercury, and the outer planets move slow, like Neptune, she expected the stars at the center of a galaxy to move fast and the stars at the outer edge to move much slower. That is what gravity says should happen. The farther you are from the central mass, the weaker the pull, and the slower you orbit. But that is not what Vera Rubin found. She measured the stars at the edges of galaxies, and to her astonishment, they were moving just as fast as the stars near the center. This was a complete violation of the known laws of gravity, unless there was a massive, invisible halo of matter surrounding the entire galaxy. Imagine a vinyl record spinning. The center spins slowly, while the outer edge moves very fast. Now, imagine a solid dinner plate spinning. The center and the edge complete one turn in the same amount of time, meaning the edge is moving much faster. The galaxies Vera Rubin observed were spinning like solid, massive plates. This discovery was revolutionary. The only way these outer stars could be moving so fast without flying off into space was if they were embedded in an enormous, invisible sphere of mass. This mass, this dark matter halo, extends far beyond the visible light of the galaxy and, in fact, contains far more mass than all the visible stars combined. So, what is it? We know what it isn't. It's not just dark clouds, because they would block starlight. It's not dead stars or planets, because we would have detected them by now. It's not a swarm of black holes, because we would see their gravitational effects on individual stars. This means dark matter is something else. It must be a new kind of particle, completely outside the standard model of physics that built you and me. Scientists call it non-baryonic matter. The leading theory is that it's a particle called a WIMP, a weakly interacting massive particle. It's massive, so it has gravity, but it's weakly interacting, meaning it doesn't bother with light or electromagnetism. It passes through you, me, and the entire planet as if we were ghosts. The only way we can see dark matter is by its gravity, and we see it everywhere. One of the most powerful proofs is called gravitational lensing. Einstein's theory of relativity tells us that massive objects warp spacetime, and this warping can bend light. When we point our telescopes at distant galaxy clusters, we see the light from galaxies behind the cluster being bent, stretched, and magnified into strange arcs and rings. It's as if we're looking through a giant, warped magnifying glass. The amazing part is this. When we calculate the mass of the visible stars and gas in the cluster, it's not nearly enough to create the lensing we observe. But when we add the mass of the dark matter halo, the exact same amount predicted by Vera Rubin's rotation curves, the calculations match perfectly. Dark matter is the invisible scaffolding of the cosmos. It formed first, creating a gravitational blueprint, and all the visible matter, the 5%, fell into these dark scaffolds to form the galaxies we see today. Without dark matter, there would be no galaxies. There would be no stars. There would be no us. That's 27% of the invisible universe. But it leaves us with the biggest, most mysterious piece of the puzzle, 68%. This final piece is called dark energy. If dark matter is the invisible glue that pulls the universe together, dark energy is the mysterious anti-gravity force that is pushing it apart. For most of the 20th century, astronomers had one big question: what is the fate of the universe? We knew the universe was expanding thanks to the Big Bang, but we assumed that the combined gravity of all the matter, both visible and dark, must be slowing that expansion down. The question was, would the expansion slow down and stop, leading to a big chill? Or would gravity eventually win, stop the expansion and pull everything back together in a big crunch, To find the answer, in 1998, two separate teams of astronomers set out to measure the rate of this slowdown. They used a special type of exploding star, a type Ia supernova, as their measuring stick. These supernovae are known as standard candles. They are special because they always explode with the exact same predictable brightness. This means that if you see one that looks dim, it must be very far away. If it looks bright, it must be close. The teams pointed their telescopes into deep space and found dozens of these supernovae. They measured their dimness to see how far away they were, and they measured their redshift to see how fast they were moving away from us. They were looking for a slowdown. What they found shocked the entire world. The distant supernovae were dimmer than they were supposed to be. This meant they were even farther away than all the models predicted. The only way this could be possible is if the expansion of the universe was not slowing down. In fact, for the past 5 or 6 billion years, it has been accelerating. Something is stepping on the gas pedal. Something is fighting against the gravity of all the dark matter and pushing the universe apart, faster and faster. Scientists had no idea what this something was. They gave it a name: dark energy. Unlike dark matter, which is a thing, a particle, dark energy seems to be a force. It is a property of empty space itself. It is the energy of the vacuum. As the universe expands, more empty space is created, and as more empty space is created, more of this repulsive dark energy comes into existence. More dark energy means more pushing, which means more expansion, which creates more space, in a runaway feedback loop. This is the dominant force in our cosmos. While dark matter holds individual galaxies together, dark energy rules the vast, empty oceans of space between galaxies, pushing them away from each other. So, here is our new picture of reality. The cosmos is made of three things. 68% is dark energy, the invisible force pushing space apart. 27% is dark matter, the invisible scaffolding holding galaxies together. And the last 5%, that's normal matter. That is every star, every galaxy, every planet, and every atom you have ever known. We are just a tiny 5% sliver of normal stuff, caught in a cosmic tug-of-war between two invisible titans. This discovery is incredibly humbling. It means our universe is not what we thought it was. It means 95% of reality is made of substances we do not understand, whose properties we can only guess at, and which we can only detect by the shadows they cast on the 5% we can see. We have given them names, but this is just a label for our own ignorance. Dark doesn't mean evil or black. It simply means unknown. The 95% is invisible because it doesn't play by our rules. It doesn't interact with light, but it dictates the past, the present, and the ultimate fate of our entire universe. The search to identify these two dark components is the single biggest quest in all of modern physics. We are building massive detectors deep underground to try and catch a single WIMP particle of dark matter passing through the Earth. We are launching new space telescopes to map the expansion of the universe and understand the nature of dark energy. We have discovered that we are, in the most literal sense, living in the dark. Why do black holes swallow both light and time? In the vast cosmos, there are objects that defy all limits of the imagination. They are the ultimate monsters of reality, invisible predators that not even light, the fastest thing in the universe, can escape. We call them black holes. We often hear them described as cosmic vacuum cleaners, swallowing everything around them. But that description isn't entirely accurate, and it downplays a reality that is far more terrifying. Black holes don't just eat matter. They bend, twist, and swallow the two most fundamental foundations of our universe: light and time. So, how can an object do that? Why is even light captured? And how can time itself be swallowed? Today, we will journey together to the edge of understanding, to the event horizon, to decode this dual mystery. To understand why a black hole swallows light, we first need to understand a concept called escape velocity. Let's take Earth as an example. If you throw a ball into the air, it falls back down because of gravity. If you throw it harder, it goes higher, but it still falls back. Every object has an escape velocity. The Moon is smaller than Earth, its gravity is weaker, so its escape velocity is only 2.4 km/s. The giant Sun has an escape velocity of 617.5 km/s. The rule is simple. The more massive an object is and the denser it is, meaning that mass is compressed into a smaller space, the stronger its gravity and the higher its escape velocity. Now, let's talk about a black hole. A black hole is what happens when an extremely large star, tens of times larger than our Sun, dies. It runs out of fuel and collapses under its own gravity. All of that enormous mass is compressed down to a single point, a point with zero volume but infinite density. Scientists call it the singularity. Imagine taking the mass of millions of Earths and crushing it into a space smaller than your fingertip. The gravity at that point is nearly infinite. And when gravity becomes that impossibly strong, the escape velocity also increases dramatically. As you get closer to this singularity, there is a boundary, an invisible line where the escape velocity is no longer 11.2 km/s or 617 km/s, but is exactly the speed of light, 300,000 km/s. This boundary is called the event horizon. This is the key. The universe has an ultimate rule. It's Albert Einstein's law. Nothing can travel faster than the speed of light. Light is the speed limit of the cosmos. When a particle of light, a photon, flies up to the event horizon, it tries to escape. But to escape, it needs to fly faster than the speed of light, because at that boundary, the escape velocity is the speed of light. And since it cannot break the cosmic rule, it cannot go faster than itself. The result? The light is trapped forever. It's not sucked in. It is simply captured in a prison from which the escape speed is an impossibility. If you are outside the event horizon, light can still escape and reach your eye, though with great difficulty. But anything, even a beam of light that crosses that boundary, is gone from our observable universe forever. That is why a black hole is perfectly black. Not a single shred of light can reflect off it or be emitted from it. It is the ultimate shadow, created by the extreme bending of physics itself. Swallowing light is frightening enough, but the way a black hole swallows time is even stranger and more mind-bending. To understand this, we must again turn to Albert Einstein. Before Einstein, we thought of space and time as two separate things. Space was the stage, and time was the clock running in the background. But in his general theory of relativity, Einstein proved that space and time are not separate. They are woven together into a single four-dimensional fabric called space-time. And gravity is not an invisible pulling force as Newton thought. Gravity is the warping or curving of this space-time fabric, caused by mass and energy. Imagine space-time is a stretched trampoline. The Earth, like a bowling ball, sits on the trampoline, causing it to dimple. Smaller objects, like the Moon, that pass by are guided into an orbit around that dimple. That is gravity. Now, imagine a black hole. A black hole is not a bowling ball. It is like a super heavy needle, puncturing through the trampoline and creating an infinitely deep well. And here's the most important part. When you warp space, you also warp time. One of the most mind-boggling consequences of relativity is gravitational time dilation. The rule is, the stronger the gravity, the slower time passes. This isn't just a theory. We measure it every single day. GPS satellites high up in orbit, where Earth's gravity is slightly weaker, have clocks that run faster than our clocks on the ground by a few microseconds every day. If we didn't correct for this time difference, your GPS would fail in minutes. If time on Earth is already running slightly slower than in space, can you imagine what happens near a black hole? the most extreme gravity well of all? Time doesn't just run slow, it almost stops. Let's do a thought experiment. Imagine you are on a safe spaceship, far from a black hole. Your brave but unlucky friend, let's call her Anne, decides to pilot a shuttle closer to the event horizon. You both have perfectly synchronized, high-precision clocks. From your perspective, as Anne gets closer to the black hole, you would see something bizarre. The intense gravity is stretching her time. You see Anne's clock start to tick, slower and slower. You see Anne's movements slow down, like watching a slow-motion film. As Anne gets right to the edge of the event horizon, from your point of view, her time will slow down so much that it nearly freezes. 1 second for Anne might be thousands, or even millions, of years for you. You would see her image frozen, right at the boundary, dimming and red-shifting, permanently frozen in time. To you, Anne never actually enters the black hole. She is simply swallowed by the freezing of time. But what about Anne? From Anne's perspective, everything is perfectly normal. Her clock still ticks 1 second at a time. She feels normal until she's torn apart by tidal forces, but that's a different story. When Anne looks back at you, she sees a terrifying sight. Because her time is slow, she sees your clock, and the clock of the entire universe outside, speeding up frantically. She might see billions of years of the universe's future flash by, right before she crosses the event horizon. And the moment she does cross it, she will be pulled toward the singularity, where the curvature of space-time becomes infinite. At that point, the concept of time, as we know it, ceases. It no longer exists. So, does a black hole swallow time? The answer is yes. From our perspective as outside observers, it swallows the time of anything falling in by permanently freezing it at the event horizon. And from the perspective of the person falling in, it swallows time by pulling them to a singularity, where the future is only a direction, an unavoidable path to destruction, and the very concept of time breaks down completely. They are places where light, the absolute speed of the universe, must stop. And they are places where the river of time, which we thought was constant, is broken. Black holes are not just objects in space. They are ruptures in the very fabric of reality. Thank you for listening to NK Fantastic, Discover Everything, and always keep questioning.